All right. Okay, let's get started. Lecture 4. So we're going to continue our discussion today of support reactions. Here I am. It's Monday. I already have my book because this is our second lecture on support reaction, not our first. It's supposed to be lecture 2. Okay, couple logistical items. So I uploaded the attendance grades from the last lecture. The homework 1 has been graded. I went ahead and posted those grades. So one thing about that, if you go to Blackboard, what you should be able to see is not just your grade, but if there were any comments that I had about your submission, you should be able to pull those up. I just typed those out. I would just check and make sure that you can see those comments. Even if you got a 10 out of 10, just make sure that you can see it. For most of you, it says correct, great job if you got a 10 out of 10, but there might have been some notes on top of that. The other thing that you should see now on Blackboard, if you log on to the main page, there should be a folder there that says older homework assignments and solutions, and you should open that, and it actually just got visible a couple minutes ago, but you should see homework 1 along with its solution. And so with every assignment, that'll be sort of the pattern. So if we have homework that was assigned Monday, that's due Wednesday, that Friday I will post the solution. And that'll pretty much be the pattern for the entirety of the semester. The one difference would be on exam days, or the days leading up to exams, you might see me post the homework solution a tad early because I want you to have it available for study. Any questions? Okay. All right. So today what we're going to do is we're going to continue our discussion with support reactions. And we're going to, if you recall in our previous lecture, that's the wrong one, this is lecture 4. If you recall in our previous lecture, one of the things I said is that we're going to take each topic and just slowly ramp it up, slowly increase the complexity or the level of detail in the problems, so that by the end we're able to handle some pretty intricate stuff. So today the star of the show is trig, or maybe a way around trig might be a way of putting it. So let's just recall from our previous lecture, we have our 3, this is what we covered sort of last time. We covered a discussion of our 3 boundary conditions, although most of our problems were focused on these 2. And that'll be the case for today as well. On Wednesday, we'll look at fixed supports. We also looked at concentrated loads, and we looked at distributed loads. Okay? And the 2 types of distributed loads that we dealt with were uniformly distributed loads and triangular loads, or linearly distributed loads. And so what we're going to do is we're just going to add a little bit more to that by looking at inclinations. Okay? So loads can be inclined as well. What I would mention right now is that we can define those inclinations either by an angle or by a slope ratio. And slope ratios tend to be a little bit more common in engineering drawings. They tend to be more common just in verbiage and in parlance. You know that, for example, getting out of the land of structures, but if you're looking at earthwork and geotech, that slope might be, that earth slope might be proportioned so that it's at a 1 to 2 slope. Has anybody ever heard that? If you're doing earthwork, that you try and don't exceed a 1 to 2 slope. Well, you don't say how many degrees that is, you just say 1 to 2. And so what that means is for every 1 foot of rise, there's 2 foot of run. And so you'll see that in the land of structural engineering as well, that inclinations are expressed via a slope ratio as opposed to an angle. And the easiest way of dealing with those is to just look at these x and y components and sort of treat the x and y components directly as opposed to using trig. So, like, for example, and I am going to draw up here on the board a little bit. So let's say I have a load, and let's say the slope ratio is, I don't know, 2 to 3, okay? Well, first off, if I have a 2 to 3 triangle, right triangle, what's the hypotenuse? So this is 2, this is 3, so 9 and 4. That's what, the square root of 13? Did I do that right? So what we typically do when we're dealing with an inclined load is we just take that load and split it up into its x and y components. So instead what I would do is replace this with just a vertical load and a horizontal load. So if this is, 100 pounds, for example, then the horizontal component is going to be 100 pounds times 3 over the square root of 13, and the vertical is going to be 100 pounds times 2 over the square root of 13. Now, some of you are probably thinking, well, wait a minute, don't you need to use trig? Don't you need to find an angle and take the sine and cosine? Well, that's actually what I just did. I just did it a little faster, okay? Remember, if you have a right triangle, what is the sine? The sine is the opposite over the hypotenuse. What is the cosine? It's the adjacent over the hypotenuse. Well, that's what I've got going on here, okay? So, for example, this 100-pound here on the x-axis is just this leg divided by the hypotenuse. Adjacent over hypotenuse, opposite over hypotenuse. So this is a much faster way than saying, okay, I'm going to take this, take the inverse tangent to get an angle, and then take the sine and cosine of that angle. You can do that if you want. I think this is a little faster, and I'm all about making problems faster and easier. And don't worry, we'll have a little bit of a practice on this here in a bit. In fact, let's go ahead and look at that. So what we're going to do is we're going to look at support reactions right now on this problem. Now, up until now, you should be pretty comfortable with doing a problem like this. What have I done? I've made the problem a little more interesting by adding an inclined load. Now, if you notice my inclined load, I have here at a 3 to 4 slope ratio. This is 3 and 4. Pop quiz, what's the hypotenuse? 5, right? And 3, 4, 5s you'll find are pretty common in here just because it makes the math a little easier. Doesn't mean that you have to have 3, 4, 5s in the real world. It just makes everything a little bit more familiar in here. Let me pull up the notebook here. All right. Okay. So I have here another simply supported beam, but here I've got distributed load and this inclined load right here. And so what we're going to do is we're going to basically try and convert this into a model that's a little bit more familiar with what we had done last time by identifying our support reactions, resolving this distributed load, and dealing with this inclined load over here. So let's do that. Let's just take it one step at a time. So let's handle this like we did before. So let's start off with support A. How many unknown reactions am I going to have here? 2. Okay. So I'm going to have a vertical reaction here. We'll call this AY. Okay. Okay, and we're going to have a horizontal reaction, and I'm going to call this AX. Now, here's where I'm going to just point something out. Okay, I'm going to take AX, and I'm going to point AX to the right. Okay, now I'm just going to make an observation about this. This is wrong. This is not going to be correct. This is not going to be the correct direction for AX. And some of you might see this now by looking at the structure. But I'm making a point by making an incorrect assumption. Because I want to show you what happens when you do, and it's not really anything to get concerned about. So I'm actually going to purposefully make an incorrect assumption right here. Now B is a roller support. I am going to go ahead and assume that acts upward here. But I just want to, again, I want to kind of slowly introduce some concepts and make sure we're familiar with what's going on here. Okay. All right, so we've got our reactions dealt with. Let's deal with this distributed load. So I have 1.4 kips per foot, and that's distributed over a length of 10 feet. So if I were to collapse that into a single point load, what would be the magnitude of that point load? 14 kips. And how far from A would I place it? 5 feet. So I can replace this 1.4 kips per foot with 14 kips and this distance here is 5 feet. Okay. Now, so far up until now, nothing should be really all that unique. But let's deal with this 20 kips. Okay. So what I'm going to do is right here, I'm going to make a note that if this is 3 and 4, that the hypotenuse of that triangle is going to be 5. Okay. And what I'm going to do is I'm going to say, okay, I've got this 20 kips, and it's sort of angled. What is it? It's angled down and to the right. Okay. So what I'm going to do is I'm going to replace that with 2 loads. One that's pointing down and one that's pointing right. And both of them are meeting at this point right here. So the loads are applied, right there. Okay. Now what I'm going to do for this vertical load, and again, this is why dealing with slope ratios is so easy, is I'm going to say this is 20 kips, and I'm going to multiply it by a fraction. And that fraction is going to be essentially the opposite over the hypotenuse, right? Because we're talking, if we want to deal in trig land, okay, this is the angle. That's the angle that we're referencing, this component right here. And if I want the vertical component of that load, it's opposite over hypotenuse. For the horizontal component, it's just adjacent over hypotenuse. So this is going to be 20 kips times 3/5. Okay? But if you're used to dealing with this in this fashion, what you can basically do is the horizontal component is just the horizontal number divided by the hypotenuse, and the vertical component, just the vertical number divided by the hypotenuse. And again, I just think this is a lot faster than trying to take the inverse tangent of 4 over 3 to get an angle, and then take the sine and cosine of that angle, just to realize that it's going to be 3/5 and 4/5 at the end of the day. Does that make sense? Again, if you feel comfortable dealing in angles and sines and cosines, go right ahead. And we are going to have some problems where sines and cosines are unavoidable. Just, again, when you can use a shortcut, let's go ahead and do it. Okay. All right, so in order to solve for these support reactions, I'm going to walk you through this one a little bit. So I'm going to handle this the same way I've done previous problems. So I'm going to start off by summing moments at A. All right, so let's sum moments at A and let's see what we get. Okay, so we're going to sum moments at A. Okay, and again, we just deal with each force one at a time. So, do I need to deal with AX or AY? No, they go directly through A. What about 14 kips? Does it cause moment at A? Yes. Does it belong on the left side or the right side? Left. And what's my moment arm? 5 feet. Okay. Okay. Now, one thing I'll mention, and I realize maybe I didn't draw this as hyper accurately as I could have. Maybe what I ought to do is redraw this horizontal load like this. So unless sort of otherwise stated in the land of structural analysis, we assume that our elements don't really have an appreciable depth when we're computing support reactions. That's not to say that isn't always the case. There are some instances where we do need to consider the geometry of the element. But really what I'm getting at is that this horizontal component and this vertical component, you can sort of treat this beam as if it's just a line. I just draw it this way so that you can see this is the actual component of the structure. So my long-winded point is going to this question, do we need to consider the horizontal component of that 20 kip load? No. We do need to consider the vertical component though. So we have the vertical component, which is contributing moment at A. So that's, let's see, that's 20 kips times 4/5. And what's my moment arm going to be? 18 feet. Okay. And then that is resisted by the moment generated by By at a moment arm of 24 feet. Okay. Did that all make sense? Everybody okay with that? Okay. So I have 14 times 5, which is 70. Okay. 20 times 4/5. 20 times 4/5 is 16. 16 times 18. I think I've got here, that's 288. So this is 70. This is 288. So if I sum that up, what do I get? I get 358. So this is, let's see if I can do that without cutting that off. Okay. So this is 358 foot kips equals BY times 24 feet. So therefore, what is BY? Make sure everybody's awake this Monday morning. And for the purpose of this class, when we start dealing in decimals and things like this, I think for kips we can say 2 decimal places. That's good enough. 14.92. So do I have a second on that?
Yep.
Okay, so that's positive. So that's 14.92 kips going upward. All right, everybody good with that? Okay, so now what I'm going to do is I'm going to sum forces in the y direction. Okay. So I list everything up on the left, everything down on the right. Okay. So what do I have going up? Well, the only thing I have going up is AY and BY. Okay. So I have AY and I have BY is 14.92 kips, right? Now what do I have going down? I want somebody to help me with this. What all do I have going down? I've got 2 forces going down. What are they?
14 kips.
14 kips.
20 kips times 14.
That's exactly right. Okay. What he said, that's very important. Okay. So what he said was, he said, I've got 14 kips going down, and I have 20 kips times 4/5. Okay, it's not 20 kips. Okay, it is the vertical component of that 20 kips. Okay, this is a really easy mistake to make, that you're not taking that and splitting it up into its x and y components. So make sure that you're considering only the vertical component when you're summing forces in the y direction, and likewise the horizontal component for the x direction. So I have AY plus 14.92 kips equals, okay, and so I got 20 kips times 4/5, that's 16. 16 and 14 will give you 30. So therefore, AY is positive, what are we getting, like 15.08? Did I do that right? I got a couple seconds in the audience. So that is 15.08 kips going up. All right. Everybody with me so far? Now, here's a couple things that are new. Okay. So first off, in our previous problems, and I believe this was probably also true on your homework assignment, the horizontal reaction at that pin support was just a formality, right? Some forces in the x direction, there's nothing going on horizontal, and so AX is 0, right? Not the case on this problem, right? Because we actually do have horizontal load, because this inclined load has both a vertical and a horizontal component. Okay? So I'm going to be formal with summing forces in the x direction. I'm going to say, all right, we're going to sum forces in the x direction, and I'm going to draw my little table, and I'm going to put everything to the right and everything to the left. Remember, when I sum forces in the x direction, I'm not multiplying by distance. This isn't a moment. I'm just listing everything out. Okay? So let's just follow this out. Okay? Do I consider AX? Yes. And I put it over here. But I don't consider AY. I don't consider BY. Just in terms of the reactions, just the AX. I don't consider anything over here, but what about this? I consider the 20 kips times 3/5, right? Now here's the weird part. Okay? This is what I got over here. What do I put over here?
0.
Nothing. It's exactly right. 0. There are no forces acting to the left. Okay? If something like that happens when you're doing a structural analysis problem, it's probably a sign that you made an incorrect assumption. That doesn't mean that the problem is folly and you have to start from square one. It just means you just probably need to pay attention a little bit. And here's why. Okay, so what is 20 times 3/5? Is that 12? Okay, so what I have here on the left side is 0, and on the right side I have AX plus 12 kips. So if I solve, what is AX? Negative 12 kips. And remember, what I said was, if you get a negative answer for a reaction, it doesn't mean that you did anything overtly wrong or you need to develop any type of distress or anything. All it means is that we made an assumption up here. This is our free body diagram, and in our free body diagram, we assumed that AX acted to the right. We got a negative answer. That means that that assumption is wrong, and in fact, the answer is 12 kips to the left. Okay? That's the answer. Okay? So if I summarize, so if I put a little summary down here, so AX is 12 kips to the left, AY is 15.08 kips upwards, and BY is 14.92 kips going upwards. This is the only thing that really matters from a final answer. Right? So here's the thing, right? I assumed that AX was acting to the right, and I got a negative answer. You might have assumed that AX was acting to the left and got a positive answer. But in the end, regardless of our assumptions, if we did the problem correctly, we both would have arrived at 12 kips to the left. Which is why, when it comes to a final answer, all I care about is the magnitude and the direction. The sign, plus or minus, doesn't really matter because the sign is just contingent on whatever assumptions we make. We might make a different assumption, but we'll get the same answer. Okay? Does that make sense? Okay. So that's why, in the end, this is all I care about. Any questions about this problem? This isn't too bad, right? Again, we just take it, just ramp it up just a little bit with each lecture. Okay. Okay. Oh, I got ahead of myself. All right. Now, so if you can incline a load, you can also incline a reaction. Okay? There's nothing to say that the ground itself cannot experience some degree of inclination. Okay? Now, we're going to do a problem here in a second with an inclined roller, but I find it's probably a good idea to take a second and discuss the math, because inclined rollers tend to be one of the first things in the class that offers a little bit of confusion. Okay? Now, I want to go back to a question in algebra regarding graphing lines. So if I have a line with a slope of 3/7, for example, how do you determine the slope of a line perpendicular to that? So if the slope is 3/7, what's the perpendicular slope? Well, it's 7/3, or the opposite sign of that. Okay? Do you remember that when you were graphing, that what you would do is you would take the fraction and you would flip it, and that would give you your perpendicular slope? Y'all remember that? Well, the same thing is true here. Okay? So I have here an example, and I have it here on the screen, but I kind of want to walk you through one here as well, here on the board. Okay? So let's say, for example, that I have a roller, and let's put it on the ground. But let's give this a very light degree of slope. Okay? So here's the slope, and let's give it a very light slope. Let's call this, I don't know, 1 to 12, right? That's a very light incline. Okay? 1 to 12 is not an atypical slope that you will see on the ground, because 1 to 12 is compliant with 88 for ramps and whatnot. So let's say we have a 1 to 12 slope and we have a roller here. Okay? So the ground, instead of being flat, the the ground is sloped just a little bit. Okay? So if the ground is sloped a little bit, what that means is that the reaction, instead of the reaction being vertical, okay, the reaction is sloped a little bit. Okay? And I propose that that reaction is going to be perpendicular to the ground. So how do I define the slope ratio for this inclined load? Well, if this is 1 to 12, this is 12 to 1, right? So see how 12 was on the horizontal leg? Now I'm putting 12 on the vertical leg. See how 1 is on the vertical leg? Now I'm putting 1 on the horizontal leg. Does that make sense? And so what I'm doing is I'm flipping the slope ratios. Okay? So if I go here on the slide, so here I used one where the numbers kind of worked out kind of nicely. So this is a 5 to 12 slope ratio. So the reason I used 5 to 12 is because the hypotenuse is 13. Okay? So the vertical leg, the reaction here, this perpendicular reaction, is going to be at a 12 to 5. So the vertical component is going to be 12 over 13, horizontal component 5 over 13. Regardless of whether you're dealing with inclined loads or inclined rollers, the denominator in these fractions should be the hypotenuse, right? So what's this hypotenuse up here going to be? What's that? 145? Square root of 145? So this vertical component right here, Fy is F times 12 over the square root of 145, and then the vertical component right here, Fx, F1 over, right? 1 over 145. Does that make sense? Probably one of those common mistakes I'll see is instead of 12 over 13 and 5 over 13, I'll see something like 5 over 12 or 12 over 5. The denominator is always the hypotenuse in both instances. Okay? Does that make sense? Okay. So I do have a homework problem like this, but I also wanted to have a problem in class actually utilizing some trig functions. But before I do, does this make sense? Anybody have any questions on this? This is probably one of the first things, like I said, this is one of the first things that gets a little tricky that you kind of have to think about a little bit. Okay. So what we're going to do on this problem is we're going to compute the reactions of this beam. And so I have a triangular load. Okay, I got a hinge support, and I have a roller support there on the right beam, but it's inclined. Okay. Now instead of doing this at a slope ratio, I've actually put an inclination degree. I've put that it's inclined to an angle of 20 degrees. Okay. All right, so let's see how we want to handle this. Okay. Now, there are some things that are going to be common. Okay. For example, okay, I've got this right here. Oh, let's do that. Let's be color coordinated. This right here. Let's call that AY. Call this AX. Okay? Now, before I deal with this roller, let's go back to this triangular load. Let's make sure we're comfortable with this. So I have a triangular load. The load is 36 feet long, and it has a height from 0 all the way up to 4 kips per foot. So if I were to collapse that into a single point load, what would the magnitude of that point load be?
72 kips.
72 kips. And how did you get that? You take 36 times 4.
Times 1/2.
Divided by 2, or times 1/2, because this is a triangle. It's very easy to just put 144. To just say, oh, there's 36 times 4. Don't forget that's a triangle, so divide that by 2. So let's put that, I don't know, somewhere about right here. Okay, and what I'll say is F equals actually write that out. Okay? And if I were to locate that, how far from A would that be located?
12 feet.
12 feet. There we go. See? Not so bad. Okay. So far, so good? Okay. Now let's deal with this 20-degree angle right here. Okay? Now, the way I'm going to handle this is I'm going to treat this sort of like a slope ratio because I think it's the easiest way to kind of visualize what's going on here. Okay? So let's draw ourselves a little triangle. And let's make this 20 degrees. Okay? Now, in order to simplify this, I'm going to assume that the hypotenuse is 1. Okay? If the hypotenuse is 1, can somebody tell me, like you can sort of ignore what's going on over here, just think of this as a basic trig problem. What is the length of this adjacent leg? How do I do that? Well, if I want to find the length of this, do I use cosine or sine? Cosine, right? Because the cosine, so here's what's going on. So the cosine so what happens with Teams? Give me one second. Somebody's calling my office line. That's what happens with Teams. Price of convenience. Okay. So if you have a triangle, the cosine is the adjacent over the hypotenuse, right? But what's the hypotenuse? 1, right? So the cosine is just equal to the adjacent, right? So what is the cosine of 20 degrees? Somebody give it to me in like 3 decimal places.
939 and 940.
So, okay. So cosine is 0.940. Okay? So, if that's the adjacent leg, how would I determine the length of this leg? If this is the cosine, what do I use here? Sine. Okay, and so what is the sine of 20 degrees?
0.342.
0.342. Is that okay? Everybody okay with that? All right. So what I've got is essentially I've got a triangle where this is 20 degrees, this is 0.342, this is 0.940, and that's 1. That's okay, right? So, if that's the case, let me rewrite that hypotenuse. That's a little confusing. Okay. So if that's the case, what I'm going to do with this reaction is actually going to be like this. Okay? So I'm going to assume that the reaction at B points like that. So this is RB. Okay? But I'm going to take RB and I'm going to split it into X and Y components. Now let's see if we're paying attention here. How much is that vertical component of RB going to be? If RB is like this, how much of RB is going upwards? 0.94, right? I take them and I flip them. This one's on the horizontal, so over here it's going to be on the vertical. So this is 0.940 RB, and this one is 0.342 RB. Now, to be clear, the independent variable is RB. Like, for example, once I solve for this component, I already know this one. So I'm sure some of you are thinking, wait a minute, are there 4 reactions? No, there's only 3, okay? Because that vertical and that horizontal component are related to one another. Again, once you get RB, you've got everything, okay? Let me sort of show you how that works. All right. Now, what I'm going to do is I'm going to treat this like we have every problem up until now. I'm going to start off by summing moments, and even with all this inclination, where do you typically want to sum moments? Probably at A, to eliminate as many unknowns. So let's sum moments at A. All right. Do we consider AX and AY? No. All right. In fact, I think I drew that table a little bigger than these. Okay. So I don't consider AX, AY. I do need to consider the 72 kips at a moment arm of
12 feet.
12 feet. Okay. So okay. And that is going to be balanced by, okay, all right, and again, my art, I always tend to do this, but remember that horizontal reaction, we're assuming that that horizontal reaction goes right through. So maybe what I ought to do is I ought to take that horizontal component, maybe what I ought to do is take this, and really where it is like right here. That's where that horizontal component is. All right. So that horizontal component, I don't need to consider that, but that vertical component, I've got not RB, but 0.94 of RB going like this at a moment arm of
36 feet.
All right. So 72 times 12, I think that's 864. Equals RB times 0.940 times 36 feet. And so, what are we getting for RB?
25.53.
25.53. Okay, do I have a second? And you might get a slightly different answer depending upon how you track your decimals. But I imagine you just use the trig function directly. So that's kips for... Now watch, here's what I'm going to do. What arrow do I put here for RB? Which way do I have it pointed? So what am I solving for? I'm solving for RB, not the vertical component. The answer actually that was RB. So I'm actually going to draw it like this. You know, because it's actually sort of... I assumed that RB was going this way. If I had gotten a negative answer, I would draw it going like that, down and to the right. Does that make sense? Okay. We're doing great on time. Okay. So now what I can do is I can sum forces in the vertical direction and the horizontal direction, because now that I have RB, I actually know both the vertical component and the horizontal component. Okay. I know both of those. These are my two independent unknowns over here. So we will sum forces. Which one do we do first? X or Y? Doesn't matter.
What?
Y. Okay. So going down, what's the only downward force I have on the structure?
72 kips.
72 kips. And going up, I have AY. And I have 0.940 RB. So what I can then do is I can say AY plus 0.940 RB is 72 kips. I know that AY plus 0.940, I now know RB. That's 25.53 kips. That's got to equal 72. And so therefore, AY equals what? Let me scroll down a little bit so you all can kind of read what's going on in that bottom part of the screen. So AY is plus what? What do we get for AY? Surprisingly, it'll come out to a nice even number.
48.
48 kips. Do I have a second on that?
Yep.
Because the thing is, if you compute the vertical component of RB, what do you get? What's RB times 0.94? It's 24 kips, right? You have a triangular load, 2/3 of it goes over here, 1/3 of it goes over here. What does the inclination of the roller do? It adds horizontal reactions both here and here. What are those horizontal reactions? Let's figure it out. We do that by summing forces in the x direction. So, the only forces that we have going to the left and right we have an assumed AX to the right, and we have a 0.342 RB going to the left. So 0.342 RB is AX, 0.342. We now know what RB is because we figured it out. That's 25.53 is AX. And therefore, AX is what? You might need your help on that.
8.73.
8.73. Do I have a second? And we assumed AX was to the right, so we got a positive answer. 8.73 kips to the right. So to summarize, sorry, I'm trying to control the scrolling. Again, magnitude and direction. And then what we'll call it is RB is 25.53 kips, and what we're interested in is that incline reaction. Okay. All right, let me stop for a sec and let everybody digest this. Did I go a little fast, or was that good? Everybody good? Okay. Does anybody have any questions on this? Not too bad, right? So a couple of housekeeping items. First off, again, I'm doing the calculations on the course content section of the notebook. Is everybody able to access that and see that? Okay. If you're having trouble accessing that on the Teams channel, let me know. This, I don't know if it's synced yet, but once it syncs, everything that you see here on the screen should be accessible in the notebook. Actually, it's synced now. So literally everything that I just wrote should be available to you now. I've got another homework assignment. Again, very similar. We have two problems. I want to show you something with these problems. So these problems are a little custom. So here's the two problems this semester. So I took one that was in the textbook and I kind of tweaked it a little bit. So there's a problem similar to this in the textbook, but I removed some things from it just because we haven't gotten there yet. We'll get to there later. If memory serves, there's a problem like this, but it has a concentrated moment, and we're talking about concentrated moments next lecture. And then I have this problem that is from another textbook, but I really like this problem. I will say that there actually theoretically is another way to do this problem. I'm certainly not going to make you do it this way, but what we did is we took this and we split it up into X and Y components. You know, that sort of was our approach in class just now. There is another way of handling this. And that is you could actually sort of take this line of action and this line of action and actually some moments right here where this line of action and this line of action intersect and solve for AY directly. Or if you wanted to be, another way you could do it is to do this in some moments up there. You could do that. I'm not going to make you do that. Or you can if you want, but the one point I would make is the structure doesn't really care how you solve it. The answer is the answer. So as long as you're following the principles of statics, everybody should arrive at the same answer, assuming you're doing the problem correctly. So just food for thought, stuff to think about. Any questions? Well, I'm going to give you 5 minutes. I'm going to pull up the code in case anybody missed it, but I will see you on Wednesday.